Hope you all are well. So today I will discuss about basic electrical engineering lecture 5, which is Norton's theorem. So before knowing the Norton's theorem, you have to know the dual theorem of Norton's theorem, Thevenin's theorem, and you have to know the superposition theorem, KCL, KVL, and how to calculate a mesh, node, loop, etc. So myself, Mr. Santanu Noskar, Assistant Professor of Electrical Department, GKCM JIS Group, and my mail ID is santanu.uit@gmail.com and santanu.noskar_gkcm@jisgroup.org. And this is my Facebook page, Being Electrify with Santanu. You can get all the lecture in my Facebook page and also in my YouTube channel. So let us discuss about your syllabus. So name of this course is Basic Electrical Engineering, course code ESW101, category Engineering Science course. ES means Engineering Science course, W means Electrical Engineering. So there are 3 hours lecture per week and 1 hour tutorial per week, and credit point of this course is 4. So about this module, there are 6 modules. I have already covered electrical circuit element RLC, voltage and current source, Kirchhoff current and voltage law, analysis of semi-complete circuit with DC excitation, superposition theorem and Thevenin's theorem. And today I will discuss about Norton's theorem. This all lecture you will get in my YouTube channel. I have a playlist of basic electrical engineering. You can go through this. So before starting this theorem, I want to share a quote by famous scientist Thomas Huxley. One day he said, "The man of science has learned to believe in justification, not by faith but by verification." Okay, so now we will discuss about the history of Norton's theorem. So Norton's theorem was independently derived in 1926 by Siemens and Huxley and researcher Hans Ferdinand Mayer, and later in Bell's lab engineer Edward Lowry Norton's, who invented the theorem, and this theorem called by his name Norton's theorem. So Norton's theorem and its dual Thevenin's theorem are widely used for circuit analysis simplification and to study circuit initial condition and steady state response. So those theorems are actually used for simplification of circuit. We can calculate those circuit by KCL, KVL also, but in a complex circuit we can use Norton's theorem, Thevenin's theorem, superposition theorem, and where what is required we have to know that, and day by day we will know the actual requirement of this theorem in this circuit. So let's start. So first, what is Norton's theorem? So Norton's theorem states that a linear active network consisting of the independent or dependent voltage source and current source and various circuit element can be substituted by an equivalent circuit consisting of a current source in parallel with a resistance, the current source being the short circuited current across the load terminal and the resistance being the internal resistance of the source network. So these are the theorem. Now I will explain about the theorem, and step by step I will solving a network utilizing the Norton's theorem. Now we can say the Norton's theorem reduces the network equivalent to the circuit having one current source, parallel resistance and load. Norton's theorem is the converse of Thevenin's theorem. It consists of equivalent current source installed of an equivalent voltage source as in Thevenin's theorem. In Thevenin's theorem we have installed equivalent voltage source. In Norton's we have to install equivalent current source. The determination of internal resistance of the source network is identical in both the theorem. In the final stage, that's in is in equivalent circuit, the current is placed in parallel to the internal resistance in Norton's theorem, whereas in Thevenin's theorem the equivalent voltage source is placed in series with the internal resistance. In last of my video I will describe what is the difference between Thevenin's theorem and Norton's theorem. Now go through the explanation of Norton's theorem. So to understand Norton's theorem in details, let us consider a circuit diagram here. In order to find through the load resistance IL, this RL is load resistance and the current going through the load resistance is IL. As shown in this circuit diagram, the load resistance has to be short circuited. As shown in this below circuit diagram, the load resistance is short circuited. Okay, now the value of current I flowing in the circuit is found out by the equation. So we can get the value of current, which is Vs by, here R2 and R3 is parallel with each other and R1 is series with those parallel resistance. So R1 plus R2 R3 parallel. Okay, this is the total I of this circuit. Now we have to and the short circuit current ISC, this current ISC is the loop current here. So ISC equals, by current divider rule we can get the value of ISC, which is I into R3 by R3 plus R2. This is, we get this by current divider rule, which is I into R3 by R3 plus R2. Now the short circuit is removed and the independent source is deactivated. Here, look here, the short circuit removed and independent source is deactivated as shown in this figure, and the value of internal resistance is calculated. So now we have to calculate the internal resistance like Thevenin's theorem. So for this we have to deactivate the voltage source. Okay, now the value of resistance internal is, look here, look from here. Okay, so here R2 resistance is series with those parallel resistance R1 and R3. So R2 plus R1 R3 parallel, which is R1 into R3 by R1 plus R3. Okay, so as per Norton's theorem, the equivalent source circuit would contain a current source in parallel to the internal resistance, the current source being the short circuited current across the shorted terminal of the load resistor. So the Norton's equivalent circuit is represented by this circuit. So we just get the short circuit current. Here we put the short circuit current as a current source and this internal resistance as a equivalent resistance, and after that we have to put the load resistance parallel with this resistance here. So this is the whole circuit. So as per Norton's equivalent circuit, the equivalent source circuit would contain a current source, okay, in parallel to the internal source internal resistance, and the current source being short circuited current across the shorted terminal of the load resistor. So the Norton equivalent circuit represented as this circuit. So finally the load current IL calculated by this equation, IL equals to ISC into R internal by R internal plus load resistor. Okay, so this is the value of load resistance. So here load current. So here IL is load current, ISC is the short circuit current, R internal is the internal resistance of the circuit, RL is the load resistance of the circuit. So that's all the explanation of Norton's theorem. Now I will discuss about some means 5 steps to solving the network utilizing Norton's theorem. So step 1 is remove the load resistance of the circuit. Okay, look here, we remove the load resistance of the circuit. Step 2 is find the internal resistance of the source network by deactivating the constant source. So we deactivate the constant source here, and now we are calculating the resistance internal of this circuit. Now step 3, now sort the load terminal and find the short circuit current ISC flowing through the sorted load terminal using conventional network analysis method. So nothing that we have to calculate the short circuit current. Okay, so step 4, now Norton's equivalent circuit is drawn by keeping the internal resistance, look here, internal resistance in parallel with the short circuit current. Okay, now step 5, reconnect the load resistance RL of the circuit across the load terminal and find the IL. So by this 5 steps we can analysis any any circuit by Norton's theorem. So very easy. If you understand the whole process, then it will be very easy to calculate any circuit by Norton's theorem. So this is all about Norton's theorem. Now we will discuss about an example math. Okay, so for example, consider our now familiar circuit from some math. Consider a circuit here. Okay, so to find the Norton's equivalent of the circuit, we firstly have to remove the 40 ohm load resistance. Consider that this is the load resistance and we have to calculate the current flowing through here. Okay, so we can calculate by Thevenin's theorem and also by Norton's theorem and also by superposition theorem, because here 2 voltage sources are here. Okay, so we have to calculate the current flowing through 40 ohm resistance. So first of all we have to remove the center 40 ohm resistor and short circuit out the terminal AB. So now this AB terminal is short circuited. So when the terminal AB are sorted together, the 2 resistors are connected in parallel across their 2 respective voltage source, and the current flowing through each resistor as well as the total short circuit current can now be calculated as, so these 2 resistors are now parallel. So now I1 equals to 10 volt by 10 ohm, because V equals to IR, so I equals to V by R. So 10 volt by 10 ohm equals to 1 ampere, and I2 equals to 20 volt by 20 ohm equals to, this is also 1 ampere. Therefore I short circuit equals to I1 plus I2, which is 2 ampere. Okay, now if we sort out the 2 voltage source and open circuit terminals A, B, the 2 resistors are now effectively connected together in parallel. The value of the internal resistance is found by the calculating the total resistance at the terminal AB, so giving us this following circuit. So we have to find out the equivalent resistance. So 10 ohm resistance is parallel with 20 ohm resistance. So equivalent resistance equals to R1 parallel R2. So R1 into, so this value is R1 into R2 by R1 plus R2, which is 20 into 10 by 20 plus 10, which is equals to 6.67 ohm. Okay. Now having found both the short circuit current IS and equivalent resistance, this then give us the following Norton's equivalent circuit. So equivalent short circuit current is IS equals to 2 ampere and resistance is 6.67 ohm. Okay, so this is short circuit source, current source is parallel, we have to put parallel the internal resistance. So far so good, but when we now have to solve with the original 40 ohm load resistance, which we have to connect across the terminal AB. Okay, now connect the 40 ohm resistance by this terminal AB. So this is the simplification of Norton's circuit. So two resistors are now connected in parallel. These two resistors are connected in parallel. Okay, so the total equivalent resistance is now, since this is R1, this is R2, so this is 6.67 and this is 40, so R1 parallel R2, so 6.67 into 40 by 6.67 plus 40, which is total is 5.72. Okay, now we know the value of current source and know the equivalent resistance. Now we can calculate the voltage across AB, which is VAB equals to I into R. I is 20 at 2 ampere and equivalent resistance is 5.72 ohm, so total is 11.44 volt. Now then current flowing through 40 ohm resistance load can be found as I equals to V by R. So V equals to 11.44, R equals to 40, 11.44 by 40 equals to 0.286 ampere. So this is whole example mathematics of Norton's theorem. So once again, and using the Norton's theorem, the value of current we calculated as 0.286 ampere, which we can also calculate by KVL and KCL. Okay, so here comes a new thing. What is the difference between Thevenin's and Norton's theorem? A very important thing. This is the dual theorem, Thevenin's and Norton's. So look here in this circuit, all are same, just difference is this. Here we have to open the source, here we have to short circuit the source, here we have to calculate the voltage source, open circuit voltage, here we have to calculate the short circuit current, and the simplification of the circuit is this equivalent resistance is series with load resistance, here equivalent resistance is parallel with load resistance. So the Norton's theorem uses a current source, whereas Thevenin's theorem uses a voltage source. Thevenin's theorem uses as resistance in series, which I have already said, while Norton's theorem uses a resistor set in parallel with the source. And Norton's theorem is actually a derivation of the Thevenin's theorem, and the Norton's resistance and the Thevenin's resistance are equal in magnitude, and the Norton's equivalent circuit and Thevenin's equivalent circuit can be easily interchanged. Okay, so this all about Norton's theorem, and this is the difference between Thevenin's and Norton's theorem. If you have the actual idea about Thevenin's and Norton's and superposition theorem, you can easily calculate any circuit by those theorem. So now next I will discuss about some reference book of your course. So first book is Basic Electrical Engineering by Ritu Sahadev. Then Basic Electrical Engineering by D.P. Kothari and I.J. Nakrat. This is the best book according to my choice for Basic Electrical Engineering. Then Basic Electrical Engineering by D.C. Kulosrestha. Then Fundamental of Electrical Engineering by Leonard S. Bobrow. Then Electrical and Electronics Technology by Hughes and revised by John Hille, Keith Brown and Ian Mackenzie Smith. Next, Electrical Engineering Fundamentals by Vincent Del Toro. So hope you all enjoy my lecture. So if you have any query, please comment in my comment box. I will definitely reply to your comment. So like, share and subscribe my channel and stay safe and stay happy. Thank you.